Kia ora. Hello, my name is Tillman. I want you to see a new app that we've built for a project called Seas, Coasts, Estuaries, New Zealand, or simply SCENZ for short. I work for NIWA, the National Institute of Water and Atmospheric Research New Zealand, and I'm presenting on behalf of my colleagues Mark Gall, Matt Pinkerton, and Simon Wood. I think it is a pretty cool app because it enables users to visualize and analyze large volumes of raster data in an easy-to-use web application for doing advanced data analysis. NIWA is one of the 7 New Zealand Crown Research Institutes. Our mission is to address New Zealand's most pressing issues and achieve economic growth by improving sectors' productivity and improving the sustainable use of natural resources. NIWA currently has around 800 employees across New Zealand. Our scientists work on a diverse range of research topics under the areas of freshwater, ocean, and climate science. NIWA also hosts one of the largest supercomputers in the Southern Hemisphere, which is used to run scientific models. So I've found that one of the key characteristics of my work here at NIWA is that we deal not only with vector data, as many other organizations, but also with large volumes of scientific raster data. So I want to give you a bit of a behind-the-scenes look at what our experience with using ArcGIS for that is. We've got everything in place to create and run innovative applications, but one thing I've found we're distinctly lacking as a GIS developer. So we had to contend with that, and this presentation is in part about how we've been able to mostly avoid custom development. Right, so before we start with the actual presentation, let me show you what I was starting out with. My colleague produced these individual folders of raster datasets, and as you can see when I click on the chlorophyll folder, there are different subfolders for different time series. I can click on the 7-day time series for chlorophyll, and there's a large number of individual NetCDF files in this. What we wanted to have in the end was this web application, and as you can see, it has a number of different tabs at the top, which the user will navigate to reach the different parts of the application. And the most important ones, from my point of view, are the time series, climatologies, and anomalies, and the shiny scenes one. So time series, as you can see, is the application that I've got open, and it's been built using Web App Builder. So what we've done here was to embed a number of individual Web App Builder apps, which were easy to build for us, into an experience builder framework. And we've also linked this application into it, which has been built using R-Shiny, and that's because my colleague has experience with R. They work together. So a user could use this application to display, visualize, and interrogate a layer such as the chlorophyll monthly layer shown here. They can animate a time series here, and the time extent goes from 2002 to present. Um, so there's a large number of individual time steps in here, but crucially, users can also use this export tool to delineate an area on the map where they want to do further analysis for the pixels behind. And remember that there's a large stack of rasters behind what we see here. It's not just one individual layer. They would trigger the GP tool, which has been set up to make an export for the monthly time series, and ultimately it creates a CSV file. It takes a minute or so, and I've done it before for this same area. I can browse to the CSV file, and this Shiny app allows a user to interrogate the statistics for the data in that CSV file. And of course, Shiny, having all those libraries for interactive graphing, you get a lot of interactivity and visual goodness out of this. And so I can choose different parameters here, and a user can really interrogate the data behind in a much more interactive way than I would have been able to easily set up in JavaScript. My presentation has 2 parts. In this first part, I want to talk about the SCENZ project and how we've designed the app to meet user requirements. Then in the second part, in order to understand the technical background and how we've set up and structured what's essentially a raster database for the web, I will explain in a bit more detail what we've done for the raster data management, and I've shown a few buzzwords here so you know what to expect. Let me first explain where this app has come from. So the project required a public-facing web app that can be used by councils, scientists, and others for reporting on the state of the marine environment around New Zealand. Essentially, we needed a tool which would be able to make large volumes of scientific raster data available in a timely manner. Besides being able to display spatio-temporal water quality data, there was also a need to analyze data in the app as well as being able to export data for analysis using external processes. This would turn data into useful information for scientists, resource managers, and other interested parties. Of course, the app had to be as easy to use as possible, which is a little harder when you know that it will be providing access to information from literally tens of thousands of rasters. The environment we've built this in has meant that we had good IT support in terms of general IT workflows, but we don't have a GIS developer, as I mentioned earlier. So that has meant that we needed to stick to out-of-the-box GIS as much as possible. We've Overall, probably achieved the goal of producing an amazing analysis and visualization tool, mostly with Esri out-of-the-box components, a bit of scripting, and a hybrid setup that also uses R-Shiny. The app, in its current state, gives users simple yet sophisticated tools to work with our science data. I won't be talking about the way these rasters have been derived from MODIS Aqua satellite data. That's probably a topic for a separate presentation. The app allows users to interrogate ocean parameters for the assessment of phytoplankton biomass, water clarity, temperature, suspended sediment, etc., and their development in time and space. Using a few simple-to-use tools, we enable users to select an area and time span of interest for efficient extraction of those water quality products, to then either download for further analysis or using online tools that provide quite sophisticated statistical analysis and graphical interpretation. As mentioned, we needed to provide analysis capabilities in the app, and we've essentially tried three different things to provide those. Firstly, the Esri WebAS widget tools, which are available on GitHub, can be integrated into Web App Builder to provide access to some easy-to-use simple analysis from image services. Secondly, analysis can be done using GP tools, using the R-ArcGIS bridge to link data for the analysis. But we found that that is quite limited as it creates static output files. So if I were to use an R library to provide a chart with the image data, that would just be printed into a static file and a user can download that. That wasn't quite what we wanted, so we decided that we will pass the data from our image service as an export file, for which we've just used the CSV file, into the R-Shiny server. And that was the perfect solution for us.
Firstly, the WebAS tools provide out-of-the-box functionality to do something with image services, such as looking at the output of a particular rendering option or choosing a time slice for a parameter. These are JavaScript-based widgets which are installed into the Web App Builder Developer Edition.
On this slide, you can see an example for one of the WebAS widgets. The IS Profile tool can be used to display a temporal profile of a point of interest. We've found that the current image service tools are rather limited, which was the reason why we decided to provide a user a GP tool to draw the area that they want to export from on the screen to create a CSV exchange file with the pixel data for the time series in the image service. The temporal evolution of individual parameters for a single location, however, can quickly be analyzed using the IS Profile tool, while external analysis is possible for larger areas by exporting the pixel values into a CSV file using other tools. I've added this slide just for reference, so you can see that with the R-ArcGIS bridge, we have been able to demonstrate how a user-selected number of pixels on the screen can be used to create charts using R. And the chart shown on the left and on the right, they're both such output, but it's static. It doesn't allow a user to interact with the graphs, and our users wanted more interactivity. So the fix, as I mentioned earlier, was to create a CSV output using a GP tool, and an example for such an exchange file is shown in the upper left corner. So this is the actual R-Shiny tool, and what we've done is to create this as a separate application which allows you to browse to the CSV file and import it for analysis and charting. It requires an installation of R-Shiny on a server and uses a series of analysis tabs, providing the power of R and Shiny with flexible dashboards to drive interactive table and graphic output. Examples of tools in the dashboard are time series, monthly trends, deseasonalized trends and forecasting, spatial maps, Hofmiller plots, etc. Any degree of analysis and complexity can be provided really for simplicity. As these tools are highly interactive, it would be, well, for us, it would have been very, very hard to replicate this functionality in JavaScript widgets. But my colleague had some experience in R, and the scientific analysis for statistics and forecasting takes place in readily available R libraries in the background. By using a combination of powerful raster database capabilities of the Mosaic dataset and the delivery via ArcGIS image services with the amazing analysis and charting capabilities of R, we think that this app showcases the best of the two worlds. In this second part of my presentation, I want to allow you to have a backstage look, as it were, of the raster data management, which was used to get the data holdings ready for the SCENZ web app. When I started to work on the project, I got given a couple of thousand NetCDF files on a network drive that needed to be made available through the app. So how do you deal with all those rasters? We ended up using Python scripts to add groups of rasters to Mosaic datasets. Then we associated so-called raster function chains with those Mosaic datasets that run predefined computations on the fly when a user triggers them or selects them for visualization. This can be used, among other things, to derive raster representations such as classifications And we can also use it to assign different rendering options, the groups of rasters for different parameters. The screenshot in the upper right corner shows how these processing templates can be accessed inside ArcGIS Pro. They basically become a part of the Mosaic dataset. Finally, we published the Mosaic dataset as a single image service that can be queried from the application. Whenever new datasets for this project are put into an agreed file location, we run a Python process that synchronizes these new datasets with the Mosaic dataset so they appear in the live raster catalog table in the web. At this point, we basically have a handle for all rasters from a database that we can interact with using queries for a range of attributes and which can be displayed using the image service as a container. The image service provides an application programming interface via a RESTful service that can be used in web applications. So let's have a look at the actual data setup quickly. What I have here is a Mosaic dataset which contains all the monthly climatology rasters. And as you can see, it is time enabled. I can animate through the temporal development here, and it shows me the rasters for that time step. It is also a multidimensional dataset, meaning the different parameters are all contained in one and the same Mosaic dataset. And to choose from one of them and display only one of them, of course, we need some kind of query. And in a database, you would, in a SQL database, you would issue a request. And in a very similar way, you can set up these processing templates which are associated with the Mosaic dataset to make a selection of a certain set of rasters. And so what we have here is the chlorophyll rendering template, but I could choose from any other one. And to show you how that's been set up, I can go to the Manage Processing Templates dialog here. And if I edit the properties on one of these datasets, you can see that it works in such a way that a request is made to a certain set of rasters using an expression which is very similar to SQL. So here I query for the variable name of CHL and product name of CHL monthly climatology. And of course, that is all part of the attributes which I've set up in the attribute table for this Mosaic dataset. And the way to do that is you can do it manually, but in our case, it was more practical to do it using the Mosaic dataset creation script.
Raster functions can be used to associate processing workflows with a Mosaic dataset. When a Mosaic dataset is published as an image service, you can associate a raster function chain with it, and this will then be used to provide server-side processing when a user requests a template to be used. So it represents the results in memory. This enables users to switch between different representations of one and the same dataset simply by activating that function from the web viewer or from another client such as ArcGIS Pro. There is an Esri GitHub repository that contains some specific raster functions that aren't part of the usual setup in ArcGIS Pro, but ArcGIS Pro actually has a lot of them out of the box.
As I mentioned, we have associated rendering options with each of these processing templates as well. And if you look at the Manage Processing Templates dialog, you can click on this Edit dialog to bring up something which looks almost like Model Builder. And you can see the different functions which I've put into this processing template. And in our case, what we've done was to remap a set of values to a certain other value and to apply a color map on that. And that's how we end up having these 20 classes. So all of that is calculated on the fly using raster functions in the processing template when you make a selection in the web application. Here's an overview from Esri that shows a schematic of the workflow that we've used to combine and publish individual raster sources into an image service. So as I said, we have multiple different ocean parameters for which we create individual child Mosaic datasets, which are what you see on the left. Each group of them has its own Mosaic dataset, and where needed, we can combine those into a derived Mosaic dataset. Then if you needed to apply any particular symbology or classification or some other raster function on those Mosaic datasets, you would associate those with the derived Mosaic datasets. Sorry, you create referenced Mosaic datasets, which you apply those on. And finally, those can be published as image services. And this workflow really gives you a perfect decoupling of individual raster sources from what you end up seeing in your service. And in the end, we actually have, we ended up having 3 different image services for our application. So with multidimensional data, with some likelihood, you'll have NetCDF data. And I would like to talk about those NetCDF data in image services. At least half of the projects I work on at NIWA use the NetCDF data format. Almost everything that comes out of the models in NIWA supercomputer is in a NetCDF file. And Esri have made great progress for those users working with multidimensional data. Because the Mosaic dataset as a container handles NetCDF data ingestion, you can add it directly into a Mosaic dataset. It allows you to retrieve data from multidimensional dataset. You can use the metadata from the NetCDF file directly. In fact, it takes care of that during the ingestion process. Live updates using the synchronized process allow services to keep running 24/7, so that all sounds like it should be no problem to use the data in Esri image services just as they are created from NetCDF data. In fact, it sounded almost too good. Sure enough, in our initial tests, we realized that the NetCDF data were a bit slow to draw or to query from, so we researched a bunch of other data. Turns out that Esri had the perfect solution for that as well. This is the process that we came up with. Some pre-processing needed to happen first. We made sure the files are renamed automatically so that the name they have, or the name they get rather, encodes the water quality parameter and the time. We later used the file name to enable searching and finding them more easily in the application, and we want to use the name string to actually apply a number of different attribute values in the Mosaic dataset table. This is required because we no longer have access to the metadata once we convert files from NetCDF into another format. Images are then pre-processed for the application by converting them from NetCDF to NASA's meta raster or MRF format. And in the process, we also compress each raster using Esri's open source LERC algorithm, which stands for Limited Error Raster Compression. Let me talk about MRF and LERC a bit more. The LERC algorithm provides faster access to imagery and rasters in the web. With LERC, we were able to define the permitted level of error incurred by the compression. So that's not like when you create a JPEG, which just compresses everything and doesn't tell you where it applies how much compression. So LERC instead is a lossy algorithm, but we can tell it how much loss we allow it to introduce. And we can tweak it to compress the rasters sufficiently while still returning data with a sufficient level of accuracy. And in our case, we were happy for a small error to be introduced as long as the dataset could be compressed well enough to improve display speed in the web application significantly. The conversion process that we've applied was run by using the Esri supplied optimized rasters script, which you can find on GitHub. So now we were able to actually display our image service nicely in the web, and it was possible to use the time slider to nicely animate through the temporal development. And using REST expressions, we were able to select the right groups of rasters from the image services that we had published. That was all fairly easy, but after some initial excitement, we found out that the analysis capability using the get samples operation wasn't actually so great using a stack of a couple of thousand of rasters. And that was when my colleague Mark actually came across an Esri blog from Julia Leonard talking about multidimensional analysis in a new format called the Transposed CRF format. And so after considering a couple of alternative options, we determined that we would need to use yet another format called Transposed CRF. This was actually not available until version 10.8.1 of ArcGIS Enterprise, which was released at the end of July 2020. So we had to upgrade as quickly as possible to be able to use that format. What we have now is one version of our image services, which is derived from the Mosaic dataset, and another one, which is the transposed raster stack. So we have duplication in some ways now, but by using this transposed form of our parent Mosaic dataset and image service, we achieved a very significant performance gain. In fact, exporting pixels using the get samples operation is now about 100 times faster than using the original image services. And that can be used to feed into the IS profile tool and also, of course, into our export tool to create the exchange file. I want to talk about creating Mosaic datasets briefly. You've probably got a sense that Mosaic datasets play a very significant role in the whole project setup. And if you've ever set one up in ArcGIS Pro, it can be an easy process, but there are also, I don't know how many, but I'm estimating a couple of hundred settings on a Mosaic dataset. So getting those right and consistently right when you have to create several Mosaic datasets or the same one over and over again can be a bit finicky. And as we have got a repository on GitHub for the Mosaic dataset creation script set up, which helps you repeatably executing the same workflow to create a Mosaic dataset, add rasters, add fields, calculate those fields, add indexes and so on. So it is a fantastic script we found, and I've extensively used and explored it, and I highly recommend using it if you have a similar task at hand. This is an example of how the configuration for a Mosaic dataset creation script can look in the XML file that you configure. Don't worry about the format. It isn't as complicated as it seems. It comes with documentation, and Esri have done a great job explaining how it's done. And as you can see in this example, we're using it to parse the name of the files and extract it into a bunch of different fields and calculating fields which we'll later use to make our database searchable.
So as I mentioned earlier, we created a geoprocessing tool that allows a user to draw an area on the screen and export the pixel values for the raster stack behind that area drawn on screen. And I've just thought I'd call out a few things that we found during the setup of this tool. So firstly, I've simply used Model Builder to set it all up, and I've created quite a few iterations of one and the same tool, and that worked quite well. An important thing was to use in-memory tables where you create intermediate output. So don't put your tables into a file geodatabase if that table is intermediate only. Use an in-memory table representation, which is going to be much quicker, and I do all sorts of conversions and adding fields, adding indexes, etc. On the fly. So that is going to be the data format of choice. Also, we had to use the Transposed CRF raster as a source for the pixel export. The original Mosaic dataset, however, didn't work quite as well. It took much longer to export from just regular Mosaic dataset. So use the Transposed CRF raster if you have to do sampling along the time axis. It is optimized for that and will be much quicker. The actual tool that I've used to set up the export itself is the sample tool, and that has an option to process the input as multidimensional. And that, of course, had to be ticked, so it would export not only one raster slice, but all of them. Another trick, in a way, was to pre-calculate a point feature class, which represents the centroids of the raster pixels that I wanted to export from. And the reason for that is that the sample tool expects two inputs, the source and the area to sample for. And the area to sample for can be an input raster, but for the web tool, there was no such raster. The user doesn't have a raster for an area. They want to draw something on the screen, and that's a graphic first, but it can make a selection from a pre-made point feature class, and so that's how I've set it up. And all of that is blazing fast and works a treat for the export process itself.
So to summarize, I just wanted to say that the Mosaic dataset is a hugely sophisticated container. It works tremendously well as a database for your raster data. But you need to do some research, and I recommend using the GitHub repositories that I've mentioned and the blog posts, and getting familiar with it isn't always easy, but when you've got it set up correctly, then you can publish your raster datasets in an image service to web enable your data. Secondly, I wanted to highlight that we found that making web applications for image service analysis and visualization is somewhat limited by the availability of out-of-the-box widgets for Web App Builder. And Experience Builder isn't much different at the moment either. So we were required to be creative with DP tools and create an Exchange file, and using our Shiny in the end has allowed us to create a super sophisticated analysis tool, and we're really pleased with the outcome. I just wanted to thank my colleagues Mark, Matt, and Simon for never giving up on the journey. It has been quite challenging at times, but perhaps if you embark on a similar journey, have a look at the resources which I'm listing on this slide. There is a lot out there, and especially for the analysis of multidimensional data on the desktop, Esri are publishing a lot of resource for that now, and hopefully as an extension to that, the server-based processes are going to be documented much more with blog posts, etc. Thank you.
This brings me to the end of my presentation. Thanks for listening, and please do get in touch with us if you have any questions about this app, or how you would use it, or if you want to set up something similar. Don't hesitate to get in touch with me. My email is here, and I'm also on GeoNet. Thank you. Bye.